Okay. Hi, everyone. So today, Kukesh and I are going to be presenting this paper, which is about learning depths from watching frozen people. So the goal of this paper was to generate something like this. So given this input video, um, you want to generate this output video where, brighter means closer to the camera. So as you can see here, um, it shows this person is probably closest to the camera, and then the people behind them get darker and darker, which makes sense. Um, and this model actually only takes in pictures. So if you're passing in a video, you would pass in the frames of the individual video. But the main goal of this paper was to create such a depth map. So why would we want to do that? There's two pretty good applications in which we could use this. So one is synthetic defocusing, as you can see on the right. You can see that the background image, once you defocus, is kind of blurred, and you can see the person more clearly, which is good. And another thing is AR object insertion. So if you have the 3D layout of a room, so you have like the depth and all of that, you basically have the geometry of the room. So you could add in another object, like you see here, this beanbag couch type thing. If you have like the geometry of that, you can literally just add it into the room as if it was there in the first place. So it's pretty cool. So existing technologies for this that exist are these two things: a depth camera and a wide baseline stereo camera. So the way that these work, so for example, the depth camera, what it does, it shines a infrared light to like nearby surfaces and everything, and calculates like the refractive index or something, and it tries to figure out the depth based off of how much like reflection it gets. And wide baseline stereo cameras, how they work is because they have these two cameras. They can actually apply a method called triangulation, which we can get into a little later. But the reason for why we don't use why it's not sufficient to say, oh, we just have these two things, why should we do anything else, is because, well, for one, these aren't common everyday like household existing objects that everyone has. You have to go out and buy them, and even then they only work in pretty specific situations. Like most of them really only work indoors and can be easily fooled outdoors. And even for the indoor situations, they have to be calibrated and all that. So it's not the best. It's actually a hassle to use these kinds of things. So before I get into what this video is, basically there's something called SLAM and MVS, which tries to address this issue, right? So SLAM is an acronym for simultaneous localization and mapping, and MVS is an acronym for multi-view stereo. Basically, these methods are existing algorithms in computer vision, which, given many views of a stationary object, we can apply triangulation to get a 3D point map. And I'll explain what triangulation is and why it needs to be stationary in just a little bit, like in like the next slide. But as you can see, if you apply the algorithm, if you apply the algorithm, you can get this house, and you can actually get a pretty nice 3D point map for that once you apply SLAM. So now into triangulation. So if you have these two frames or these two pictures of a stationary object, you can take this elbow point and that elbow point and kind of draw a line like that, as you can see, and you can kind of figure out where the elbow is in the overall thing when you're trying to create a depth map. It's easy because these things are stationary, so you can literally just follow. Every point corresponds to another point. Like you're guaranteed that every point corresponds to another point, which is very useful. But if the object is moving, that's not necessarily the case. So the elbow point that was initially correlated here and the elbow point here, they now meet when you apply the same triangulation algorithm. They meet at this red point here, which is obviously not the elbow that we're looking for. We're looking for this second yellow point. So triangulation doesn't really work on on a moving object, which is why it's actually pretty hard to get this on people. Um, we don't really have or there for a very long time there really wasn't a lot of data available for people on this kind of stuff. It's obviously easier for buildings in which you can take multiple views of something. So I mean, obviously here comes in the time where, you know, you just want to train some model on some data and, you know, create a depth a depth map. That's what people are trying to do using machine learning, using multi-view supervision, and you can get something like this input and this predicted depth map, right? But it's obviously highly dependent on the training data. So the training data that existed, these are uh, two of the very prominent ones, Kitty and the NYU data set. So Kitty, what it did basically, because it was so hard to manually uh, um, get every one of the to manually make a depth map of like many different scenarios. What they did was they put a bunch of points on a screen and asked the users to, or the people who are making the data set, to just say which one is farther, which one is closer, or like which one is farther away, which one is closer to the camera. And this way you can kind of get a sense of like the general terrain, you know, what the general depth should be for the entire video. The NYU kind of did a similar thing. But yeah, this obviously, as you can see, it's not going to be too applicable for people. But there actually is another data source or data set, I guess, that you can consider that wasn't really used, and that's literally the internet. So you can literally search up a picture of, for example, the Colosseum, and you can get a bunch of these images of the Colosseum, but at completely different angles. So as you might assume from what I've been talking about previously, you can literally apply the SLAM and MVS techniques to generate a 3D point map of the Colosseum based off of this data. You can just scrape this data and literally just apply that algorithm and run it. So you can get something like this. And it's actually pretty nice. So all of these things down here are the triangulated the pictures that would triangulate to form this 3D point map. So yeah, if you apply MVS and you scrape similarly for more than 200 plus landmarks, you can get more than 130K images. And you know, once you apply MVS, you can get these colored maps that kind of give you the depth or what it predicts. As you can see here, it's kind of noisy. The images aren't entirely full. Like you can see, there's a lot of black patches and everything. That actually doesn't matter, because the way that CNNs work, it'll like smoothen it out. So even if you don't have some data in specific pixels, it'll work just fine. So if you you know, run the depth predictions on using this another model called MegaDepth, you can get these smoothened out versions, which are a lot less noisier in comparison to these images, as you can see. So why can't we get this for people? Well, it's basically the same argument that we made before, right? So for example, if you have a statue, it can actually recognize this. The MVS algorithm can actually recognize the statue, because it's very likely that a lot of images of that same statue from many different angles have been uploaded, because it's a popular statue. But it's very unlikely that that someone at the same exact time that these two folks in the bottom took a picture of themselves, that another person you know, took a picture of them from a completely different angle and uploaded it to the same page. It is just very unlikely. So as you can see here, the MVS algorithm actually, it gets the building behind it. It just doesn't get the people. So if, hello? If there was a way to you know, get some data of stationary people for multiple views, that would be great. And what that actually is the Mannequin data set. So a while ago, a couple years ago, I think 2016, the Mannequin challenge was super popular. The trend is basically, so I'll play the video in just a bit, but as the trend is that people will be basically stationary throughout the entire thing, and you have one person moving a camera, you know, quite a few different angles, and you can get, you know, views of a person or all the people in the video of them being stationary, and you can get like multiple views of that. So if you see here, everyone is basically stationary and doing some sort of pose, whatever it may be, whether it's standing, holding a basketball, holding a calculator, doing something, some unpredictable human action. And they're all stationary, so you know you can get a lot of views from just the same thing. And even if they move a little bit, it's fine. It's not a big deal. So you know, if you get the training data set using these videos, you can get something that looks like this. So if you started with those things, you can apply MVS and get these those images as you saw over here. Yeah, these images. So I'll pass this on to Kukesh now.
Yeah.
Explain how the model is trained and so on.
Okay, so let me share the screen. So as Venkatesh was saying, so it's pretty clear that like the MVS tends to work better on places where the object is stationary, and we were able to get multiple point views of that object, like in case of a building. With our current data set, what happened is the humans have become kind of a stationary objects, and in order to get the multiple views, we have a video from which we can extract those frame by frame images, and from that we can easily calculate the depth map based on the MVS. So right now we have RGB images and the depth images using the MVS. So what would be the most straight way to get a depth map from the RGB? It's like basically use a regression network like encoder decoder based regression network. You pass in the RGB image and having MVS depth as the target, and you get the output like the predicted depth. So what you can see here is the output depth is much more smoother than the MVS depth. So this basically corresponds to the loss function that they were using. For example, the loss function they were using is a combination of MSE loss and gradient loss as well as a smoothing loss. So MSE and the gradient loss much focused on getting the correct depth values, while the smoothing loss try to smoothen out the values. For example, if you could see the MVS depth, there are a lot of places where there is no depth. So basically what this smoothing loss does is it tries to assume that the pixels which are very close by to one of the depth pixel should have a similar kind of a depth. So in that way, it is able to smoothen the output. So what is the problem with this model? So if you could see here, the first image is obtained using RGBD, which is like from a depth camera. And as you can see here, the person's hand is very much visible and distinct, as well as the table edge and as well as the teacup. But the depth predicted by our model didn't seem to take into account of the table edges as well as you could see, the teacup and also the hand. So why it is not performing well? So the thing is, it is not getting enough information. So as we all know, the more information you give the model, it's going to perform better. So this is the kind of approach the who wrote the paper took. And I'm going to show the output which they obtained with further refining of the model and giving more input to the model. So the last part is the model with more inputs that is given by the author of the paper. So the final model is able to predict the edges as well as the teacup and as well as the hand movement. So what are these inputs they are giving? So if you go into it, the first is called a pseudo-depth map. So to put it in perspective, the pseudo-depth map is a lightweight version of the depth map. So it is not too accurate. So what they do is, since we are getting the depth map from the video, we can easily get the reference frame and the target frame. So if you could see, the reference frame is the bottom one and the target frame is the topmost one. So in order to calculate the motion between two images, we could use something called as optical flow. So what does optical flow do is, it calculates the movement of pixels or the brightness from one particular frame to the other. So it basically gives a direction in which the motion is happening. So if you could see this particular image, you can see the people in the background seem to have a lower value, while the people in the upper image seem to have higher value. This is because the motion of the camera is from the back towards the front. So in this way, we obtain the optical flow. And the second thing, what we need to calculate the depth map is called the pose of the camera. So basically they obtained the pose of the camera from SFM, and that is a structure from motion. By combining this, they obtain a lightweight depth map. And as we know, like the humans with motion tend to cause error in our system. And our aim is to get the exact prediction of depth for the humans. So what we do is we get rid of the humans using a mask RCNN, which basically mask out the humans from the image. And what we are left with is just basically the depth map of the environment. It is not too accurate, but it gives a sense of like how the environment is static relative to the humans. And the second input would be nothing but the mask that of the humans. So what we are going to pass is the RGB image and the human mask and the pseudo-depth mask. And we are going to use the same kind of the loss function. And so the output of this, you can see the output of this model here, right here. So it should load. So as you can see, these four are the models which are currently state of the art for the depth model. And the Dawn seems to be doing very well in static data, but when it comes to the detecting depth from motion, all the state of the art things fail. This is because they were not trained on such kind of data. So since this particular model is trained on this particular type of data, which takes into account the motion, it is able to do better in detecting, for example, the person, even if there, like say, a lot of motion involved in the picture. So what are the applications? So before the applications, if I could show you, the first one is the depth obtained by the depth camera. And the second one is the depth obtained by Dawn. And the next one would be the depth obtained by Demon. And following is the depth obtained by a single RGB image model. And the last is our full model. So as you could see, the last model seemed to be outperforming all the model and coming very close to what we could get with the RGBD. So this is kind of a huge improvement than what we have now. And what are the applications of this is called, first is synthetic defocus. So to put into perspective, what is synthetic defocus? We are all aware of the portrait photos, right? So when we talk about portrait photos, what we basically do is, based on a static image, we are able to get the depth of the image, and using that information, they were able to focus our body front and based on the depth. But it is not possible on videos. This is because it is very difficult to obtain the depth from videos. But with this approach, now it is really possible to do a portrait mode on videos. So this might come very soon. So if you could see, we can able to zoom in and zoom out based on using the depth alone. And one of the other application is like in painting. Usually, if you want to remove a particular person or a particular thing from a video or an image, what we usually do is we either use GANs to remove them to create a synthetic image. But here in this case, they have not used GANs or any synthetic approach. They basically use the information that is obtained from the depth to fill in the hole after removing this particular person. So one of the things which I observed, which is not discussed in the paper, it might help is, like we all know Tesla is using cameras to calculate the depth. So right now, it is very difficult to calculate the pedestrians from the camera alone. So they might be using a camera in combination with radar, but with the current approach, their model might become more robust because now the camera also takes into account of the motion when the people are moving. So that's particularly it for our paper. Do you have any questions? Should be. Yeah, guys.
Cool. Okay. Is it?
Have you implemented, or did they provide an implementation of the model? Have you tried to use it?
Yes, what they have given is a pre-trained model of it. So the basic implementation is very simple. All you have to get the two data, and it is basically a similar like encoder decoder structure, the kind of what do you call the basic encoder decoder with a regression task at the end. So it's easily implementable, and also there is a page in GitHub called Mannequin Challenge from Google. So this basically covers what they did in the paper.
Yeah, but the thing with the GitHub is that so it does provide the single view model and the model with the multiple inputs, the full view model. But the thing is, you don't really have the data. If you wanted to pass it on your own video or your own images, for example, with the multiple view, you don't have the human masks or the masked pseudo depth. You only obviously have the RGB frames from your own image or your video. So in that way, you can only use the single view model that they provide, and it performs reasonably well too, as shown before. But yeah, they only give that unless you wanted to run your own mask RCNN and
Optical flow pipeline.
optical flow type thing. Yeah.
Gotcha. So the mask would be the second one, right? And how would you get the third thing? What is that?
So what you do is you get two different images. For example, one is a reference image and one would be the target image, right? Based on the video. You pass them to a network called flow network, which basically calculates you the optical flow. So you get the optical map, and then you estimate the camera position using structure from motion. For example, if you are able to know which position the camera is used while taking the picture, based on these two, we can get a lightweight depth map. And after getting the lightweight depth map, what you could do is you can use a mask RCNN to get rid of the human mask. And there you go, you have the pseudo-depth map.
Gotcha. Is the optical flow, is that also available?
Yeah, it's available. It's called FlowNet, I guess. It's called FlowNet. It is available with the pre-trained weights.
Gotcha. Awesome. Thank you. Great work, guys.
Thanks. Any more questions? Okay, I guess not. Okay, thank you, everyone.
Yeah, thank you, guys.
Yeah, okay, bye. Have a nice night or morning or whatever time it is.
See you guys.